award in 2013 from the Elettrosynchrotron Limited. So through his career, the main focus of his research has been on physicochemical phenomena and organic materials, including thin film growth, self-assembly, interface electronics, and chemical reaction. And since the last 10 years, he became an international recognized expert in a new field, which is at the limit of physics and chemistry. It's called on-surface synthesis, which I think we are going to learn a lot now. And here he explored surface-supported chemical reactions for the synthesis of functional molecular materials as graphene nanoribbons, as we see here. So, Dimas, your turn.
Thank you very much for the kind and detailed introduction, Martina. Okay, yeah. So thanks again for the kind and detailed introduction. And yeah, so I'll be telling you something today about the chemical stability of zigzag edges in carbon nanostructures, like these graphene nanoribbons that I'm showing you here. And just to start with, I want to start picturing. So what is it actually? What is the effect of zigzag edges in carbon nanostructures? And without going into the details, just an easy way to visualize it is just comparing the electronic properties of molecules with and without zigzag edges. And I start with this molecule here, for example. So this is the chemical structure, and I just show you here the energy level diagram of its molecular orbitals. And so these are the occupied orbitals, the empty orbital. So this is the highest occupied molecular orbital, or HOMO, the lowest unoccupied molecular orbital, or LUMO, and it has a notable band gap. Now, okay, so if we make this molecule slightly larger, what we see, just adding one more ring, but still we see that the edges of the molecule are basically this armchair shape. What we see is that the HOMO-LUMO gap shrinks slightly. This is as expected. You increase the size of the box, let's say, that confines your electrons in your molecule, and then, well, their energy decreases slightly, and the HOMO-LUMO gap shrinks accordingly. But now think what would happen if you take just the same size of the molecule, just ordering the atoms in a way that we have zigzag edges instead of these armchair edges. And the result is actually this. We have the same number of rings, the same number of atoms, but now we see that the band gap shrinks very much. Actually, it shrinks so much that this HOMO and the LUMO, they kind of like slightly hybridize, and so the occupation is no longer like a full occupation of the HOMO, and the LUMO is fully empty. You have partial occupations of either, and this can also be pictured in a way like this. So basically what you have is a contribution of other resonance forms to this hexazine structure as shown here, in which you have two radicals. So you have basically a radical array character for these molecules. And of course, you would not expect this in principle to happen because, I mean, it's energetically costly to generate radicals. But on the other hand, what you gain is some kind of energy stabilization due to the fact that, well, if you draw this closed shell structure, as you see, there is only one Clar-sextet. And by Clar-sextet, what I mean is one of these hexagons in which you have three double bonds. You see, for any acene, you only have one, whatever the length is. So you have one, you can draw it at different places, but all the other hexagons have only two atoms. And this is actually a very stabilizing construction. So here, this destabilizes the structure, but you gain a second Clar-sextet. So this is actually what makes, what allows this structure, let's say, to contribute to the, or both of these resonance structures to contribute. And so basically you see increasing the zigzag edges or going from armchair to zigzag edges, what you're actually doing is you're promoting some open shell character in these molecules. The same happens actually if you draw a different molecule, again, with the same number of rings. I take 6 rings, you order them differently. In this case, the open shell character is even more extreme. You can actually not draw this chemical structure by any means without including two radicals. I mean, you cannot satisfy the valence 4 of these carbon atoms without drawing two radicals somewhere. You can move the bonds around, but you always will need to draw two radicals. And if you look at the calculated energy levels, you actually have these two zero energy states here. And what this actually does is it endows the molecule with a spin density. That is, we have these two singly occupied orbitals. So basically, we see where this is a high spin molecule, a spin 1 molecule. So we see when we go from armature to zigzag edges on the molecules, we kind of create spin density and the molecule with magnetic properties. And the same does not only happen for molecules, let's say zero-dimensional objects, the same also applies to larger extended structures like in graphene nanoribbons. So you have a two-dimensional flat graphene sheet, and if you confine it, if you cut a narrow stripe of it, if you cut it in such a way that the edges are along the zigzag directions of the carbon lattice, then what you see is also here that let's focus on the dotted lines. These are the simple tight binding calculations. You see that the valence and the conduction band, they go all the way to the charge neutral point. So once again, you have these low energy states here. This is an unfavorable situation to have high density of states just at the Fermi level. So what the system actually does is it opens up a gap by opening this, or by creating this spin polarization, by creating this spin polarized edge states, what we call. So this is basically a picture, just without going into the details of what exactly drives the spin polarization, but I'm just showing you with some examples that the more zigzag edges you have, the more easy it is to have some spin polarization in your carbon nanostructures. And another way to see is just focusing, as in this case, on graphene nanoribbons of different structures. And that's, for example, what they did in this nice paper from the group of Steve Louis. Here you can see band structures of graphene nanoribbons as a function of the edge orientation, which can go either from having the zigzag oriented edges to having armature oriented edges, or any chiral orientation in between. So if you have only armature edges, then your band structure is a semiconducting band structure. You see there is a gap opening between the valence band and the conduction band. This is what we saw for the zigzag nanoribbons. In this case, you have this high density of these low energy states here, and then these are the states that undergo spin polarization. Now, if we go to any intermediate orientation, which are all of these, we always end up having some segments of zigzag orientation, some segments of armature orientations, and whatever amount of zigzag orientation segments you have, you always still have some low energy states at the Fermi level. And again, all these structures in turn undergo spin polarization. The more states you have of those is, well, the closer your nanoribbon orientation is to the zigzag direction. But basically, as soon as you have any zigzag segments, you are in any of these structures, you have low energy states, and those bring about this spin polarization. Now, this is actually interesting for many types of applications in quantum technologies and spintronics and so on, but it also has a downside to it. And basically, it's that these low energy states, well, or the spin density is nothing but radicals. It's basically from uncoupled spins, and this confers the structures very high reactivity. And this is actually what makes these molecules to have been studied. I mean, only more or less recently. I mean, there were already hypothesized about purely carbon nanostructures that were magnetic already in the 1950s. People were thinking and calculating properties of molecules like triangulene, as I was showing you before, but they have only been realized more or less lately because they couldn't be synthesized. And a way to undergo this reactivity problem is actually by this more or less recent direction of organic chemistry that has been developing, which is on-surface synthesis under ultra-high vacuum. So if you do, this is our, let's say, organic chemistry lab. And but now, instead of having a solution environment that is more or less uncontrolled, we have ultra-high vacuum. And this allows us to have this very inert environment. And then in a very inert environment, these structures are no longer susceptible to being attacked and react with anything else, because there is nothing in our UHV chamber. We're at pressures of 10 to the minus 10 millibar, or that range. And in addition, we have these surface sensitive, I mean, this allows us to use the surface sensitive characterization techniques. So the way this organic chemistry lab works is then a little bit pictured like here. We have some reactant molecules that we start with. We get these from our real organic chemists, our collaborators. And then we put some of these powders into evaporators that we attach to our ultra-high vacuum chamber. And then we clean a substrate in there, and we deposit the molecules onto the substrate. Normally, this is done by evaporation. There are also other means, but we most commonly use evaporation of these materials. Then, if you basically evaporate the materials under ultra-high vacuum and place the substrate on top, the molecules, they land on the substrate, they absorb, and then you can activate their reactions in this two-dimensional space on your surface. And again, there are different ways to trigger these activations. But well, the most common one is actually to do it thermally. And then, okay, so you change whatever to whatever structures, and then you can come with your surface sensitive characterization techniques and probe these materials at the single molecule level. And I'm just showing here, for example, some electron tunneling, some tunneling current, for example. And but you can also use other types of spectroscopies. And this all allows us to get a very nice resolution and information about structural, chemical, electronic, and magnetic properties of these materials. And okay, now that I said a little bit how we do this, I go back to the structure, because a lot of the work that we have been doing is on graphene nanoribbons, as I was showing you before. And in particular, what I'll be focusing on today is on nanoribbons of this particular edge orientation. So it's some intermediate between the zigzag and the armchair edges. And we see we do have these low energy states. So in principle, you expect these nanoribbons to have these spin polarized edge states. Okay, so then this is basically how we synthesize them. So all this blue box here is the job of our organic chemist collaborators. And what we get from them is actually these three molecules, for example. And these are the molecules that we get in powder that we introduce into our UHV chamber and sublime onto a surface. And then on top of it, in particular, these works have been done on a clean gold 111 surface. And then after certain annealing treatments, what we manage is to transform these ribbons into these different, or these precursor molecules into these different ribbons. And these are just some representative STM images of the different samples. And we see, so these ribbons, they all share the same edge structure. So it's basically a chiral graphene nanoribbon in which you have 3 zigzag segments and 1 armature periodically alternating. And we only change the width, right? From these, let's say, from 8 zigzag lines across the width, 6 and 4. Okay. So now you can take these different ribbons and you can characterize them, as I said before, and you can measure the properties of them. You can actually resolve their chemical bonding structure. If you take your scanning probe microscope and you functionalize it with a CO molecule, then and you approach very close, then you can actually resolve these chemical bonding structure. You can see the hexagons more or less nicely for these differently wide ribbons. And not only that, you can do spectroscopy. And that's what we do here. So we can go to one specific point, as marked here, and take a conductance spectrum. And then the conductance that you get, which is plotted here, is a signal that is actually proportional to the density of states at that particular position. And then basically what you have is something that is proportional to the density of states as a function of the energy of the electrons that you're using for the tunneling. And then if you go to these wider ribbons, you see that you have a very strong intensity here just at the Fermi level, which actually refers to this high intensity that we had. So these are the states that undergo spin polarization and that have this radical character. The same happens actually for this intermediate ribbon width. But then we see that when we narrow we have the narrowest ribbons, then basically a band gap opens and we have the onset of the conduction band, the onset of the valence band. Here we actually have a band gap of around 0.7 electron volts. This is also confirmed by calculations. These are the band structures of the ribbons with the different widths. So these are these narrow ribbons, and then we see this is the intermediate ones. These are the wider ones. In both of these cases, we see this low energy states, and but here we see that this band gap opens. Okay, so then we have a band gap of 0.7 electron volts. And this is actually a very nice value in principle. For example, if you wanted to make transistors out of it. And then we thought, okay, so that may be actually a very interesting structure for potential applications. And here we have interesting band gap value. We have no low energy states, and consequently, we expect no radical or spin density, no reactivity. So we could make devices out of it. So we synthesized some of these samples, we sent them to collaborators of ours, and the answer that we got is that nothing worked at all. So obviously there was some problem somewhere, and then we were a little bit disappointed, but we thought, okay, so let's see why it doesn't work. And so maybe they're not as stable as we thought. And then what we did is to take one of these samples, and this is basically how it looks as grown. So this is the sample we get. This is a high resolution bond resolving image of these ribbons. And then we take this sample and expose it to air. And after exposure to air, we put it back in vacuum again, cool it again in our low temperature microscope and measure. And after air exposure, this is what we see. So we see a mess. We don't see anything. That's just because air is so annoyingly dirty and all kind of crap absorbs on our clean gold surface. So we cannot recognize much from here. And then to get some idea about what has happened to the ribbons, what we need to do is to take this sample and under UHV anneal it. And then if you anneal it, you basically desorb most of those small molecules that have co-adsorbed. And then the kind of structures or the kind of samples that you end with is these. These are still dirty samples, let's say, for our standards, but you can already recognize the ribbons at least. And you already see just from the large scale image that here we had beautifully straight ribbons. Here they become curvy. So this already gives you some hints something is happening. And in fact, when you take the high resolution images, you see that these hexagons, many of them are distorted, they change in brightness. So all of these are associated to chemical changes. So these ribbons have degraded when going from here to here. And obviously the electronic properties have degraded as well. Okay, now the question is, what has driven this degradation? And because we have exposed them to air, but we have also annealed this sample. And we have annealed them in the presence of all kinds of molecules next to them. So we may just be activating some reactions here of this crap that is co-adsorbed with the ribbons. So we wanted to get a little bit a better insight about what is happening here. And not only that, we wanted to make better controlled experiments, because air is a complex mixture of gases that changes from my lab to any other lab around the world. So these are the most common components, but the ratio varies from place to place. And so the idea was, okay, let's do more controlled experiments. Let's try to get rid of this annealing step. And we can do that by exposing our samples only to low pressures of high purity gases. And then, okay, which gases do we choose to test? Well, then we just choose the most reactive ones, or not the most inert ones, because we don't expect these to do anything or to react in any way with our ribbons. So we're left with oxygen and water. And then this is what we did. So I start with the water case, and this is how the ribbons look after exposing them to 800 langmuries of water. So that's basically 3 × 10⁻⁷ millibars. So this is still high vacuum for 1 hour. And okay, so we can see that these samples are already much cleaner than what we had before. So we can more or less characterize them relatively well. And if you take a closer look at these ribbons, what you see is that they are slightly different from what the pristine ribbons were. You see that in every unit cell, you see like a brighter line here. And actually, if you look at the bond resolving images, you see that where you have these brighter lines, these hexagons, they're like larger and larger than these here. So there is something going on at these positions, at these carbon positions here. The question that we had is, I mean, we lack chemical sensitivity with our microscope, and we were wondering, so is this water actually hydrogenating our ribbons? So are we having these extra hydrogens here, or are we oxidizing the ribbons? Let's say, is this OH part binding to those atoms? And then we didn't exactly know how to differentiate this. And then what we decided to do is some control experiment. And then we use, instead of water, ethanol. With ethanol, we would expect a similar reaction to happen. And then if it was a reduction, what was going on, then we would end up with the same product as with water. If it was an oxidation, we would have this additional tail, carbon tail here, that would be more easily distinguishable with our STM. So we took our ribbons, we exposed them to ethanol in the same amount as the water. And these are the images that we get. And we see that every second unit cell, we see this slightly larger rings here on the sides. So this actually tells us, okay, so both with water and with ethanol, what we're having is this reduction. So from here, we already learned something. So basically, the central carbon of these zigzag edges is the most reactive side. And the way to understand this qualitatively is looking at this picture. As I said before, Clar-sextets are stabilizing, and the chemical structures, they like to have as many Clar-sextets as possible. I highlight the Clar-sextets here in gray. If you take the pristine nanoribbon, you have 2 Clar-sextets per unit cell. I mean, you can draw them differently, but you can always have only maximum 2. Now, there is a way to increase the number of Clar-sextets by adding 2 radicals. And actually, calculations on this unit cell show that this resonance structure contributes with 12% to the total. So that is, even though it's a predominantly closed shell structure, you still have some contribution of this open shell, a minor contribution of this open shell character. And we believe that this is sufficient to make these ribbons so reactive, and in particular at these positions here. Then on the other hand, another curious thing that we see is that only every second unit cell is affected. And we have some studies about that as well, but I'll not enter into that today. Okay, so basically, so we see that water reduces our ribbons, but I mean, this chemical change is reversible. I mean, you can just go, this is our hydrogenated ribbon. You see these larger hexagons at every second unit cell. Well, here we have 2 pristine unit cells in between, but in general, it's every second. And you can go with your tip to one particular position, and you can put electrons. If they have a sufficiently high energy, they will dehydrogenate this extra hydrogen, and then you will end up with a rehybridization back to an sp2 configuration of that carbon. And if you draw then the chemical, I mean, then what you get is a very funny contrast here. Well, it's particularly funny because this is a funny color scale, but you see you get a much brighter intensity around here. You still see the hexagons and everything, but this density is actually related to this radical state that we're creating here. So this is basically the structure that we start with. And then when we rehybridize these into an sp2 configuration, you end up with this radical in a pz orbital that is very easily accessible to our STM. So that's what we're seeing here. And you can also do it with any of the other hydrogens that we have around, and then you can kick them out, or you can also do it thermally. I mean, if you have this structure and you just anneal it, you get back to the pristine nanoribbon. So basically, we see water. I mean, these hydrogenated sp3 carbon atoms, they can be reversibly converted back, and by tip-induced dehydrogenation or annealing, which means that water only causes a reversible reduction of the chiral graphene nanoribbons. So what is actually destroying our ribbons when we expose them to air is probably not the water, but something else. So then the next thing that we tried was then going for the oxygen. So this is then, so we exposed a ribbon to oxygen, again, still in high vacuum for 2 hours. And then this is how it looks like. You see, this is now much messier. We see a lot of, I mean, everything is much more dramatically modified than it was before. And if we look with some more detail into the different types of defects that we get in our ribbons, this is how it looks like. So here I'm showing you these bond resolving SDM images. So this is a current image. We can also measure, let's say, forces. So this is just with a different type of measurement with our scanning probe. You can just as well resolve the chemical bonding structure. And this is the simulation, how we would expect these images to look like. And this is the corresponding structure. Okay, so this is the reference. This is the unchanged graphene nanoribbon. And what we see when we make a statistical analysis of the different types of defects, it's that the most common defect that we observe is actually this one. And this is how it looks. And these we associate to ketones at these positions. And these make up actually for 70% of the defects, so really the large majority. But this is actually not all. We have also other cases. We have cases in which the ketones are coordinated to a gold atom. In this case, this is a little bit different. We have an extra hydrogen at this position. We also see cases in which you see this elongated structure coming out. These are actually hydroxyl groups. So we can recognize a number of different defects, and we also have other types of defects, all of which we see reproducibly. We can distinguish them, but we were not able to assign them to particular defective structures. But we see, well, we can still learn a number of things from these. So first of all, again, here we see that the most affected atoms are always the central carbon atom of these zigzag edges, and this I already explained why. Then we also see that the ketones, I mean, as I showed you before, are the most common oxidation product. We see that the defects normally affect both sides of a unit cell, and this relates to the fact that if you affect one side, on the opposite side, you are creating a radical. And then that radical is, of course, much more reactive, and anything that is around will much more readily attack there at that position. And then another very important thing is that these changes are irreversible. I mean, you see that many of the defects, they actually have notable changes in the carbon backbone. So there is no going back to the original form by annealing. So the oxygen really affects the ribbons in an irreversible manner. So there is some need for protection measures here. And this is what we tried to attempt. We thought, okay, how can we synthesize these ribbons and protect them? I mean, when organic chemists, conventional organic chemists in solution and so on, have protection problems, they use this protection deprotection method. So they protect them with some chemical functionalities that they can remove afterwards. So we thought, okay, let's try to do something like that with this on-surface synthesis approach. And this is the idea we came up with. Okay, so we know which are the most reactive carbon positions. So let's try to protect them. Let's try to protect these central positions. So for example, with hydrogens, just some extra hydrogens here. And if you have extra hydrogens, then you are actually at the same time creating a larger number of Klarsig-Stedts. This will open the band gap of your material, and this will make it less reactive. And then if you can do this, this may be protected from degradation. And we know that hydrogenation, we can easily go back and forth. So this would be an ideal picture of a way to protect and deprotect in a controllable way. Okay. And actually, if you think of it, this is more or less what we already have with our water-exposed graphene nanoribbons, right? It's only that we have it only every second unit cell, but okay, we thought, let's give it a try. And then we took this sample, we exposed it to oxygen, and unfortunately, there is no protection effect at all. So the ribbons, they degrade severely. So this was unsuccessful, but then we thought, okay, so let's try something else. And then what we wanted to try is to hydrogenate those structures more heavily. And so we take our initial sample, and now we expose them to a flow of atomic hydrogen. So we have a hydrogen cracker, we dose our atomic hydrogen into our UHV chamber, and this is then how the ribbons look afterwards. So this looks really messy. This is because here, not only the edge atoms, but also the interior atoms, they hydrogenate and then they rehybridize from sp2 to sp3. And then the whole structure becomes buckly, non-planar and everything. That's why it looks so messy here. And well, if you actually hydrogenate the samples only very lightly, then you can see a little bit how the hydrogenation starts. And this is what I show here with some non-contact AFM images. And you can already see that the most the most commonly hydrogenated places, that is where it starts, are actually, again, these same positions, these central positions here. Then the next, that's because this is where the highest radical character is on these structures. The next most common positions are these central carbon atoms, basically these two here. And that's because these carbon atoms are the only ones that you can now modify without breaking or affecting any of these stabilizing Clark-6 states. So this is where it first hydrogenates, this is where it hydrogenates next, and then anything else comes and you end up with this mess. Okay, but now the important question is, are these structures now stable to air? And what we do is we take this sample, we expose it to air as we did initially. Afterwards, we put it back into ultra high vacuum. We anneal it to get rid of these extra hydrogens, and we check, have they irreversibly degraded by the oxygen in air? And the result is that 90% of the unit cells are unaffected. This is our ribbon after air exposure. So basically, we were very happy because we have successfully protected and deprotected these chemically labile ribbons. So this made us very happy, but then we thought, okay, so this is cool, but let's try to use also, I mean, let's see whether we can also apply different ways of protection. And then instead of putting hydrogens at those positions, at those most reactive positions, let's see whether putting ketones, which we know is anyway the most common oxidation product, whether we can form ribbons with these molecules and whether these are stable. And then this is the job of the organic chemists. They synthesize these different precursors, and then we take them and we try to form ribbons. And it actually works. This is a large scale image. This is how the ribbons look like with a more detailed characterization. This is the structure. We see we have a larger number of Clark-6 states. This opens the band gap of this material. And then the question, so are these ribbons now stable to air? And the answer is yes, they are. These beautiful images are actually taken after air exposure and annealing. And we see there is really nothing modified. So we were very happy to see that we can now synthesize air-stable chiral graphene nanoribbons. Actually, not all the ribbons look like this. We have two types of ketone functionalized chiral graphene nanoribbons. In some of the cases, the ketones of one ribbon are looking at the hydrogens of the neighboring ribbons. And so they're basically held together in islands by hydrogen bonds. In other cases, the ketones, they're basically looking at each other. And there is something in between there, which we know are actually gold atoms that come from the substrate that we use. And if we look at the electronic properties of these different ribbons, this is what we see. So I'm showing again. So these are these conductance spectra, as you know. Now, I mean, the signal is this proportional to the density of states. And then these are the pristine ribbons without any ketones. This is the band gap I already showed you before. We see how the band gap opens dramatically when you have the ketones and this larger number of Clark-6 sets, as I was showing you before. not only, so the band gap opens, that's because of this different conjugation pattern. The mid gap position shifts down, that's because of the electron withdrawing nature of the oxygens. And then when we have the gold coordination, we see that the band gap shrinks again and shifts farther down. This is actually because of the charge transfer between the atoms and our ribbons. But the question is, okay, so what is actually, why is this band gap changing from here to here by this gold coordination? And actually calculations confirm this. So this is the band structure for the pristine ribbons, for the ketone functionalized ribbons, and for the gold coordinated ketone functionalized ribbons. We see that from here to here, the band gap opens a lot. We see that from here to here, it shrinks again. And we also see that the most affected band is actually not the conduction band, which, I mean, its dispersion is not so strongly affected, but we see that the valence band becomes much flatter when it coordinates to the iron. We can also see it when we map out the spatial distribution of the orbitals of that band. When we go basically to the valence band onset, we see that it changes a lot from here to here, while the conduction band does not change so much from here to here, right? So this basically all fits together. But now, why is this, or I mean, an intuitive idea of what is it that is actually driving this change here in the band structure? And this we can get from the chemical, basically from the bond lengths. And so this is a bond length analysis of the different structures. And I guess you cannot read these small numbers, but this is just color coded. So here, basically, you probably see that it's a more or less homogeneous color. So the bond lengths are more or less similar. When you go to the ketone functionalized ribbons, what you see is that there is this dark blue bond here. So this is a very short bond. And this is the carbon-oxygen bond. This is this double bond. And this is a very short one. That's as expected. And then you see these very dark red bonds here. These are very long. And this is very long because these are single bonds here, right? And then, so you see, we have much larger variations. But now when we coordinate these ketones to gold, what happens? Well, basically, that the coordination to the gold takes some of the double bond character of the carbon-oxygen bond. So it basically elongates that bond. By elongating that bond, you actually make these bonds a little bit shorter. So this is no longer so double. This is no longer so simple. So you get to some intermediate level between these two cases. And that's why also the band gap gets to some intermediate place here. But okay, this was just like a sidestep. But now we're worried about, or we're thinking our main aim was actually the chemical stability of these ribbons. So we saw these and these are equally stable. They're both not affected by air, but it's still the question, can we transform these ribbons back into pristine ribbons? Into ribbons like these, which have a band gap that is actually, let's say, in a technologically more interesting range. And then what we do is, okay, so this, well, yeah, this just gives you some idea about the sensing ability of the ketone side groups. But then what we do to check this reversibility is, can we deprotect these protected ribbons with the ketones? And what we tried here is basically, again, a similar trick. We take these ribbons and we expose them once again to a source of atomic hydrogen. And then this is how the sample looks. After doing that, once again, it becomes buckly, three-dimensional, ugly. But then after this, if we take this sample and anneal it, what we end up having is just dispersed, normal, pristine graphene nanoribbons. So we see, I mean, 80% of the unit cells are not affected. So we were very happy to see that we have, once again, successfully protected the ribbons and deprotected them afterwards. And actually, not only that, this is also a nice potential way that can be extrapolated to many other molecules. And this is just some example. I mean, this is a stable, easily synthesizable molecule that we can now, with this same trick, convert into this high spin nanomolecular magnet here, as we published here recently. So this same approach can be used like as a new synthetic tool to make very interesting structures. Okay, and so this is about the protection, deprotection, but as I said before, I mean, it works, we're very happy with that, but we're always left with a certain amount of defects. I mean, it's not many, but there are some defects. And the point is that even these defects are actually very interesting. And so now what I'm going to tell you about is a little bit focusing now on the remaining defects that we end up having in our structures. And that's because, well, if we have, for example, a missing ketone in a ketone functionalized ribbon, this defect is actually a radical, right? So a radical is a spin, so there is some magnetism to it, and we can have one or we can have more than one. Or if we have pristine ribbons and we oxidize them, then on the opposite side of the oxygen, there is a radical. I mean, we saw that before as well. And then we can have pair of radicals and we can measure the interaction between those spins. And then we can see actually how do they interact at different positions with respect to one another, different distances. We have chiral ribbons, so one side and the other side could be different. They can be on opposite sides or on the same side. So this is somehow all this kind of structures that we paid attention to. And then we start, first of all, characterizing a single defect. So this is a ketone functionalized ribbon in which there is one of these ketones missing here. And then as you see in our scanning tunneling microscopy image, you see this bright contrast here. As I said before, this is just the fingerprint of this extra pz or unpaired pz electron that is somewhere at low energies. And then this gives us this strong signal. And if you take a conductance spectrum just at this position, then you get a signal like this. And from here, well, you can see this peak here. This is actually the onset of the valence band, or well, let's say the HOMO, because even your valence band is due to the finite size of your ribbon. I mean, it's discretized, so let's call it a molecular orbital. So this is the HOMO associated with the onset of the valence band for an infinite ribbon. This is the LUMO, which would be the onset of the conduction band for an infinite ribbon. And then we have these in-gap states. And you can map them out, and you see that this state and this state, they actually look the same when you take an electron out of it or when you put another electron. And that's because they are basically the same orbital, just when you take the single electron out or when you put a second electron in. So this is a state that is occupied with a single electron, a singly occupied molecular orbital, singly unoccupied molecular orbital here. And this is actually the calculated spin density that this state has. So if it has this spin density, we should be able to see some magnetic fingerprint of it. And in STS, you look at that when taking a closer look around the low, I mean, with the low energy spectra. And basically what we see is that we have this zero bias resonance that broadens anomalously fast with temperature. And this is associated to a Kondo resonance, which is an indirect but unambiguous fingerprint of the magnetism of these states. So basically, we confirm we have the magnetism of this S1/2 defect here. And then we can do a similar type of analysis of the single defects in the opposite case, where we have pristine ribbons and just with one ketone, let's say, at a certain position. And then we see again the same. So we see the HOMO, the LUMO, we see these in-gap states, we see the Kondo resonance, how it broadens with temperature. We see that they look the same when you put an electron in or when you take the electron out. This is the spin density. Now here it's important to realize that the spin density extends more into neighboring unit cells in this case than in the ketone case. And this is actually because the band gap of these pristine ribbons, let's say, next to it is much lower. And then these magnetic states, they can hybridize with the conventional states, and then they can basically have a larger extension. And but maintaining a clear chirality-driven asymmetry. So we see that the spin density extends more in one direction than in the other. So there is a clear fingerprint of the chirality. We see that the SOMO-SUMO gap is much lower in this case than in the other case. That's because the states are much more extended. And then the Coulomb gap, so basically the distance between the SOMO and the SUMO is the Coulomb repulsion of having one electron or having a second electron in there. And then because you have a more extended state, it's lower in this case than in the previous one. Okay, so this is about the single defects, but then we can have defect pairs. And this is actually the most interesting scenario. And then you can get a lot of different structures and a lot of different pairs, and you can extract from these conductance spectra the different alignment, relative alignment of your spins. And I will not go into all the details of all the spectra. I'm just going to compare selectively some of them. And so I'll start, for example, just taking these two. And here what we're comparing is two defects on pristine nanoribbons, in which we have one ketone functionalization here and one here, and the same here, with the same chirality, but at different distances. In this case, we have 2 unit cells, unaffected unit cells in between the defects. In this case, we have only 1. Now, what we see is, let me first explain what these spectra actually represent. Here we see, let's say, these steppy structures here, and these step structures actually come in or an increase in the conductance here. It comes from the fact that at these energies, you are allowing the electrons to flip. And by doing that, you're opening additional possible conductance channels, and then your conductance, your measured conductance increases. So the energy at which this happens, it basically gives you an idea of what the energy or what is the energy that you need to flip those electrons. And then you see that this, when they are closer, the energy that you need those electrons is much larger, which is kind of expected. But I mean, it's nice to corroborate it, how you let's say lower the exchange correlation when you bring the defects farther apart. Now you can also compare 2 defects that are at the same distance but with different chiralities. And so in this case, these are 2 ribbons, pristine ribbons, in which we have 2 of these magnetic defects, and then we have 1 pristine unit cell in between. But in one case, we have 1 chirality, in the other case, we have another chirality. And we saw before that the spin density is actually not symmetric, it's also chiral, so it extends more in one direction than in the other. And then if the spin density extends more in the direction away from the other defect, then the 2 spins, they talk to each other less, and that's why the energy to make them flip is lower. If the spin density extends in the direction of the other defect, the 2 spins talk to each other much more, and then you need a higher energy to actually flip them. So this is another nice insight that we can get from here. We also see that we have a larger exchange correlation in lower bandgap graphene nanoribbons. So if we compare 2 defects with the same chirality at the same distance, and the only difference is whether in the separation between them, whether we have these ketone functionalized unit cells, which have a larger bandgap, or whether we have the pristine, which have a lower bandgap. Now, as we saw before, if you have a lower bandgap, your spin density can extend more. And then if it extends more, the 2 spins talk more to each other, they see more each other. That's why in this case, we see this exchange coupling. In this case, we just see a condo. In this case, we just see a condo peak. That's basically these 2 spins, they are independent of one another. They don't really talk to each other. And then the last curious thing that we saw is that in general, in any graphitic structure, you would, graphitic structures, they can be seen as 2 interpenetrated hexagonal lattices. So it's like a bipartite lattice, and then 2 hexagonal lattices in which, let's say, red and blue, and in which each atom of one lattice only binds to atoms of the opposite lattice. And now, because chemical bonds, if you have a chemical bond, you want 2 electrons to be antiferromagnetically aligned. If they're ferromagnetically aligned, you don't bind them. And this actually makes that you, in general, you assume the spins on one lattice to be the opposite orientation from the spins on the opposite sublattice. Now, this also brings me then to the point that if you have a defect on one side and all on a ribbon, the same side is always blue, and you have a defect on the opposite side, you would expect them to be, well, blue and red, and they will be antiferromagnetic. If they're on the same side, you would expect them to be ferromagnetically aligned. Okay, what we see is that when we compare these two cases in which we have 2 defects with the same chirality, with defects on the same ribbon side, we can, from fitting these spectra, we know that in this case, our two spins are ferromagnetically aligned as expected, but in this case, they are antiferromagnetically aligned. And this is actually very surprising. And now what we see is that DFT confirms the experiments, but mean-field-Hubbard tight binding model does not. And in this case, in principle, you just, this extraposition of the ketone, you just model by putting on well, it's one additional carbon side. I mean, one additional PZ electron that you add there, but there is no chemical information about that. And then what we thought is, okay, to make a counter experiment, theoretical experiment, and let's calculate how the alignment of these spins would be if we have a situation that is really more similar to this tight binding case. So you just add another carbon, I mean, another electron, but on a carbon atom. So you add basically a CH2 group at these positions instead of the ketones. And then it would be just like the ketones, you would have a double bond between these two carbon atoms. So the conjugation pattern as you draw it would be similar. But then in this case, you see that both DFT and mean-field-Hubbard tight binding agree on this more intuitive scenario in which if you have the defect on the same side, they align ferromagnetically. So there is some, the reason for these defects to align antiferromagnetically is somehow univocally related to this different chemistry of the oxygen atom. And then the idea was, okay, let's see whether we can still model it with these simpler methods. And then what we do is we compare the band structures of the DFT, which is these gray curves, to the tight binding, to the conventional tight binding model. And we see that there is actually a pretty large disagreement. And then we thought, okay, let's see whether we can make them a better fitting just by changing the tight binding parameters just on these oxygen atoms. So let's say putting some chemical information into our simple tight binding model. And we do that by simply increasing the hopping amplitude across this, oxygen carbon bond. And this you can easily explain because this is kind of intuitive because that bond length is much shorter and then you would expect a larger hopping amplitude. And you also put some on-site energy because it's the oxygen atoms are more electronegative, and this makes it more favorable for the electrons to sit at those particular positions. And then basically by changing this, as you see, you get a much better fit now with the blue to the gray curves. And if you do that, you can see that actually, if you play around with these parameters, you see that changing the oxygen on-site energy, you can change from having a preferred antiferromagnetic ground state to having a preferred ferromagnetic ground state. So basically, we get this now relatively nice understanding, not only of the chemical interactions between these spins, but also an easy way to model it with these more or less simple tight binding modeling parameters. And this now brings me to an end. So I just showed you that graphene nanoribbons with zigzag edges are not stable to air exposure, even for predominantly closed shell structures. That whereas water causes a reversible hydrogenation, oxygen causes irreversible graphene nanoribbon degradation. We have developed ways to apply this protection, deprotection strategy to on-surface chemistry under UHV conditions. And we have gotten a very nice understanding of the structure-property relations with regard to exchange correlation interaction of radical states. And now, after this, I just want to thank all the people involved. Many people have been working on these projects. I want, first of all, to start thanking all the people here from our community here in San Sebastian, from DIPC and the CFM, and then also our collaborators from, let's say, from the Czech Republic who have been doing calculations in part, or Bruno and Alejandro have been also doing some of the AFM measurements. Sophia and Thomas also here in San Sebastian have been doing also calculations. Yeah, so this is all experiments. These are calculations performed here. And then our molecular precursor, I mean, the people who synthesize the molecular precursors that we use is from the group of Diego Peña in Santiago de Compostela. And then just end thanking you for your attention.
Thanks, Dimas, for the presentation. If you don't mind, I start. We have 2 questions here from the chat. So the first one is from Alex Bittner. He's asking, though air contains only traces of hydrocarbons, their sticking coefficient is 1. So I would expect not just oxidation and water absorption. Of course, this is depending on the air, but specifically lab air in a surface science lab might contain some oil. Do you think you can get oil on the surface?
I mean, we definitely see all kinds of crap after air exposure. And I've never deposited, let's say, oil, but oil has many aliphatic chains, and we definitely see aliphatic chains on our surface. So it can very probably be oil as well, yes.
There is another question from Elisa Jimenez. She's asking, is it possible to obtain fully unpassivated zigzag edges without any hydrogen or other adsorbate?
Is it possible to obtain fully unpassivated zigzag edges? I do not fully, I'm not sure whether I understand the question completely. I mean, you can get fully unpassivated just by synthesizing those structures under ultra-high vacuum. That is something that has been, I mean, I was showing the case of zigzag graphene nanoribbons, which we haven't grown in our lab, but they have been synthesized. So there is only just the hydrogen atom saturating, let's say, the sp2 character of those carbons. I mean, that has been obtained. I don't know whether that's...
But without any hydrogen or other adsorbate, I mean, hydrogen we always have.
I mean, if you have no hydrogen, I mean, then you end up with not only basically the PZ radicals, but you would also have the sigma radical, and those sigma radicals will definitely somehow bind or partially bind at least to the surface. So actually there are studies, previous studies in which they did how was it? I mean, it was Micromi was doing something like that, and they were removing the edge hydrogens of those ribbons, and then they saw that they were actually tilting the edges. They were tilting towards the surface. They were curving, and that's actually associated to this binding of those sigma radicals then to the surface, creating this slightly bent structure.
Yeah, this is actually the question. Then will they reconstruct necessarily?
Yeah.
Yeah. Yeah. Please. Yeah.
I have a question according to the Kondo measurement. What do you the zero bias anomaly? You see it as a conductance in one ribbon or on the gold surface at all?
We see it at the position of the defect. So we see it on the ribbon. We don't see it if we go far away from there on the gold.
Okay, you contact the ribbon? Or?
No, this is actually a tunneling experiment. So yes. We have the gold substrate, we have the ribbon on top with our unpaired electron with our spin, and then we go with our scanning tunneling microscope tip. So basically, we have a 2-electrode circuit in which one of the contacts is our microscope tip, and the other contact is our substrate, and that's the current flow.
Okay.
And that's where we see this Kondo resonance.
Yes,
and I have another one. Can you control the ribbons in such a way that you could put them parallel to each other on the gold surface?
Yes, we have actually done that. I mean, if you want to do it macroscopically, what we have done is to use, instead of flat surfaces, you use periodically stepped surfaces. You use a miscut angle with respect to the flat 111 surface, you put some angle, and then what you end up is periodically spaced steps. And then the ribbons, they just like to align with those steps. And that's actually that we have done with these very ribbons. So that's, yeah, I didn't tell it here, but that's something that we have been doing. And I mean, that's on a, let's say, macroscopic scale, but you can also, these ribbons, we also manipulate them. I mean, we can move them with our microscope around on the tip. So if you wanted to, I don't know, to play around and then put two ribbons next to each other parallel to specific ribbons, I mean, you can also do that just by manipulation. That's a little bit more tricky, but it's possible.
Thank you.
Okay, so we have more questions here from David Fija. Thank you very much for this great talk. Fascinating. Could you elaborate a bit about the plausible role of God 101 in the magnetic exchange coupling?
The role of the gold 111 on the magnetic exchange coupling. I don't really know, but I mean, what I know is that the exchange coupling energies that we measure experimentally fit pretty nicely with the calculated ones for freestanding ribbons. So from there, I expect the gold not to be affecting too much, but whether it does to some extent, I don't really know.
There's another question on this way. Does God 101 play any role in the reactivity of graphene nanoribbons? If they were on sodium chloride, would they be equally reactive?
I think it would be pretty much the same, yes. I mean, it would be even more messy because, so I don't know, well, maybe, I mean, the intrinsic reactivity of the ribbon, I would expect it to be the same or higher if you put it, because I mean, after all, the interaction with the metal will always be more stuff. I mean, the interaction with the metal will be somehow stabilizing. So somehow whatever spin density that you have or radicals that you have, I mean, it's somehow at least partially stabilized by the interaction with the gold. If you have it on sodium chloride, first of all, it's much closer to a freestanding ribbon where you really only have these pure unaffected spin states, and those would be more radical, more reactive. And besides, but still, I think it would be comparable. But another thing that may affect it is that if you expose the ribbons on top of salt to air, and these salt layers that we normally use also in our lab, also they are not stable to air. I mean, these single layers that we use, and then I don't know what the chlorine or the sodium would additionally do to the ribbon, so that it may be an even messier sample than what we already have.
Okay, Aaron wants to ask something. Aaron, you can ask your question. I don't know how this goes. No, you can't hear me, I think. No.
Come down from your office, Aran.
The thing is that I don't know. The problem with the link. Can I ask a question? Yeah. Okay, the one of Aaron. Can you try to reversibly hydrogenate, then irreversibly oxidize, and then remove the nitrogen as a way to control the oxidation, at least partially?
Again, so you hydrogenate?
Yeah. So can you try to reversibly
hydrogenate,
yeah.
then irreversibly oxidize,
then
and then remove the nitrogen?
The hydrogen, I would say.
Remove the hydrogen, okay.
As a way to control the oxidation.
At least partially. I guess that would be possible. Yeah, I mean, that we haven't tried, and I guess the level of control wouldn't be very high. But yeah, probably it's a way to oxidize partially, and with some degree of control over the oxidation level. Yeah.
Then there is Bo Chen. He would like also to pose a question. Bo, you can speak. Okay. Okay, he wrote it. I don't know. So the surface is a polymerization of organic molecules into graphene nanoribbon. This is a reaction one would not expect to occur in solution, but it occurs on surface. What is the driving force on this surface reaction, on the surface reaction?
I mean, the synthesis process that we use for the synthesis of these ribbons is basically a two-step process. Early slides. So these are the precursors that you have, well, or these, but it's basically the same. In a first step, you have a polymerization. This is so basically through these positions with the halogen carbon bond. This is a reaction that is very commonly applied also in solution chemistry. This is Ullmann coupling. On surfaces, actually, the people call it Ullmann coupling, although chemists often complain because on surfaces it's slightly different and shouldn't be called like that. But I mean, basically, the coupling through this carbon-halogen bond, this can be done in a similar way, and I think the driving force is the same in solution and on a surface. The next step is, once you have a polymer of these structures, to planarize them, to get rid of these hydrogens. That's something that probably wouldn't occur in solution. And here, I think the driving force is basically that when you are on a surface, these molecules, they just like to be planar. I mean, the interaction with the substrate is very stabilizing. And then obviously they interact with the substrate more if they lie planar on the substrate than if they are in a three-dimensional space. And that is, in my opinion, what what allows for these cyclodehydrogenations to occur. I hope that answered the question.
So I don't know if there are more questions here in the audience. And if not, here also there are no more questions. Then we thank the speaker. Thank you, Dimas, for the talk.